So Rupa and I are delighted to be here to talk to you about an idea. We hope that this idea has an impact on our cities. Our cities are in high demand, but also are affected by climate change, pollution, and we think that ideas we're thinking about are based on resilience, performance, and perhaps even more importantly, the environment. So we're going to talk a little bit about human nature. We're going to talk about maybe an idea of changing human nature, becoming more aware of how we might design and build for these principles. This idea started here, Jinmao, and a complicated building, but it had some pretty simple concepts that we could build a building that had a system that connected the core of the building to the outside at 3 levels along the height of the building with these very large trusses, outrigger trusses. You've heard of this many, many times since, but at the time that we were developing this, there were significant challenges. Most importantly, we wanted to build this building from the bottom up. And in doing that, the core and the columns moved much differently under creep, shrinkage, and elastic shortening. So we introduced pins into the system to allow these trusses to move freely during construction, not adding additional stresses to the trusses. And we did it by using these really simple principles of statics and allowing mechanisms to be created by the use of pins in circular holes and slots. Those simple ideas turned into working drawings, fabrication of the components. You get a sense of scale with the man standing next to one of the connections of one of the trusses for these outriggers. Building's pretty successful. Many of you have been here. We've had conferences there. You can stay in the Grand Hyatt. We're really proud of what went into the building to make this building happen. And lately, people are having some fun with this. Rupa and I are not going to be doing this, by the way. This is the Jinmao Skywalk that was recently opened. So if you go to Shanghai, I'm not sure if we encourage you to try this, but anyway, there's an option to try this if you'd like to at this building. We've seen some behavior that we'd like to learn from in Kobe in the mid-90s. We had some significant damage to buildings, mid-height collapses, lack of ductility, lack of natural behavior. So we wonder about what is it that influences us in design? And sometimes it's not tall buildings. Sometimes it's indigenous architecture. The Isle of Chiloé, I visited this place, and I found that these churches that were built in the early 1900s survived the great Chilean earthquake of 1960. And I was convinced they survived because of these wood dowels. Friction fit connections that didn't use mechanical fasteners, that were fixed for most of the building's life, but when the demand got quite high, they either rotated or slid. They dissipated energy and they protected the building. So what is it about motion? If you believe that everything is in motion, that buildings are not static, but they're dynamic, and this motion exists at small and really large scales, and the environment and the change and the dying of glaciers and sea level rise, this is real. It's undeniable. So how can we come up with systems that perhaps can have an impact on this condition? The image on the right is one of 2 places in the world. This particular place is in the Arctic. It's a subterranean storage facility that stores every seed known to mankind. So we wonder, what if we're not able to deal with these environmental changes? So what can we do incrementally to have an impact?
This idea of the Fermi paradox, which to recap is pointed out by Enrico Fermi back in I think it's in the 50s when he pointed it out. But it is interesting to note that we don't see evidence of civilizations beyond our own. And that's not to say that there aren't any, but we don't see any evidence. And we've looked a bit, and we've used radio telescopes to look for radio transmissions, and we haven't found anything. So there are many solutions to this. One of them might be that complex life is much rarer than simple life. So it could be that microbes, simple biochemistry, that single-celled organisms form across the universe. They could even be present on Jupiter's moon Europa,
solar system,
Saturn's moon Enceladus, or subsurface on Mars, but really anywhere where there's liquid water and some kind of stability and some kind of driving force in the sense of geological activity. So it could be that life is common but complex life is rare. Or it could be that civilizations don't last long, which is one of the terms in the so-called Drake equation, first written down by Frank Drake. So the idea that an industrial civilization has a short life, perhaps because our technological power in terms of affecting the climate or developing nuclear weapons and all those challenges that we face today, perhaps that runs ahead of our political ability. So we don't have the political skill to run a planet, or just control the technology. Maybe technology and engineering and science runs ahead of politics. I would like to say, because engineers and scientists are a little bit brighter than the average politician, so therefore it's inevitable that science and engineering run ahead of politics, and therefore we can't control the demons we unleash.
So joints in buildings, just like the joints in our own human body. During a seismic event, there's a high demand on the beam column joint, which means it wants to rotate, just like a shoulder joint that we have. In a conventional moment frame, this rotation takes place with yielding of the base material in the panel zone, in a designated zone in a reduced beam section. And this was the first initial concept for which Mark almost got fired because he placed it in the working drawings without having it tested. This concept is basically just having that moment frame beam to rotate about the pin, with sliding to occur just at the top and the bottom flanges. And from there on, we have consistently tried to include this pin connection in a beam column joint in a moment frame, or be it at the ends of the brace for the eccentric brace frame. But since we are trying to rotate this beam column joint about the center pin, it makes more sense to have curved surfaces. And here is the evolution of the design, where we have curved plates that are clamped together by bolts, and they rotate at threshold friction. It rotates about the pin when at a preset threshold friction at force when it's exceeded. This can be easily controlled by clamping of the bolts. To the left, we have a regular conventional moment frame when subjected to high moment demands, it yields the base material. To the right is a pin-fused joint, which rotates and dissipates energy through friction. It's unusual for a firm like us to go for a patent in the building system, but we did put forward our technology up there, and it was patented, which shows that it was the first initial patent that, or first innovation that we had created. So the next question is, how do we erect it in field? And here, for this particular case, we had two halves of the beam that connects, that's brought into place and then clamped together, and have the splice joint right at the center. This first initial concept was tested at Stanford University. We were looking to answer two questions. One, is the sliding coefficient of friction similar for a curved plate? Second, what value does the pin add to the system? After the test, we have validated the slip friction coefficient remains intact for even the curved surfaces. And the pin is really important. It helps in guiding the sliding to occur right on the curved surfaces, and it distributes the forces along the bolts that's all placed along the curved surfaces. Here's the joint. Pin that comes together and is clamped with the bolt. And it's important to note that for a low seismic event or for a wind event, the connection is intact. Only when a particular moment, a threshold moment is exceeded, does this connection slide and dissipate energy. And this is a full frame with this beam column joints in place. So in a tall building, we know stiffness governs, and a brace plays a very important role. So here is a connection where we have included a brace slip joint within the two halves of the braces. The idea is to have the brace slip initially, and then when it locks itself to the end of the slots, it redirects the force level, and it lets the moment rotation occur at the beam column joint. And then we tested this concept again in UC San Diego. It was a full frame test. Each of the joints had been tested independently, along with the brace slip joint, and finally, we tested the whole frame. Just to let you know, for a conventional design, a frame is designed up till 4% story drift. A beam column joint is designed up till 4% story drift, but for this frame, it was tested all the way up till 9%, twice of what would you expect in a conventional moment frame. And here's how it comes together. Just an important note that the slip in here occurs on the vertical plane. So this system eliminates the center splice connection that we had. Now, extending this idea into a reinforced concrete shear wall system. This is a link fuse joint where we had a prefabricated piece where it connects two diagonally opposite slots through a bolt. And again, when the threshold shear force is exceeded in the link beam, they slip. And you have a joint that dissipates energy through friction. Now you can include this prefabricated piece in a reinforced concrete shear wall, in a steel plate shear wall, or even in a EBF or in an eccentric braced frame link. The joint end, they're connected through a center bolt. And here's the joint. So the tests were performed at Stanford as well as at UC San Diego using brass shims. And there were concerns about cold welding, electrolytic corrosion. And in order to mitigate that, we came up with non-metallic shims that are used in brake lining pads in aerospace engineering. These are the systems that can be easily placed in, and this was tested in E. coli Polytechnic lab, and we have reliable friction coefficient with 3 levels of velocity, which are basically tied in to the building period.
So there we have it. It's a start, we think. There are different ideas for different applications, and if you want to learn more, there's some ideas out there. These are a couple of publications just came out. One is a general publication about the work that we've been up to, including this work, and the second is about tall buildings and about architecture and how we think that structure and architecture relate to one another. So they're resources. What's next? So, we think that there's a broader application to cities, the idea of sensory fields, that we know when the earthquake is coming. We know when the storm is coming. And can we somehow take that information and apply it to things that we normally tuck away in drawers and don't use anymore, structural analysis models, that could, in fact, inform our buildings interactively. magnitude and direction of load, and perhaps we change the characteristics of joints, the materials within joints, that changes friction, that allows some joints to move more freely than others, minimizing materials, minimizing the impact on the environment. So that's what we have. We thank the council for this award, and we look forward to the development from others on pushing some of these forward and lessening the impacts that we see that are so severe to us and generate such a need. So thanks for listening, and that's what we have for you today.